Right, good morning. So let's begin again. The lecture is getting recorded. So today we will continue our discussion on convolution. So very briefly, last time to recall, right, we defined what the convolution is. So we said that the convolution two waveforms. Let's say I'm using different notations just to show you how to write it in a general way. So this is a waveform one. Let's say A of t is complex valued and B of t is complex valued. So two complex waveforms. Waveforms, or you can think of them as signals, right? So individually, these two waveforms have their own shape. So let's say I plot the two of them as a function of time. This is my x of A of t. And let's say this is my B of t. So A of t and B of t are two functions, right, defined in time. But I can define a new function. Let's say I'm going to call it new name. I'm going to call it C of t. It's defined as A of t convolution B of t. Symbol for convolution. It's a symbol. So in signal processing, when you see this asterisk, right, in the computer keyboard, you see the asterisk for multiplication, but in signal processing, asterisk is reserved for convolution. If you want to multiply, right, let's say E of t is the product, then you write it directly like this. So this is the product. But when you see this star or asterisk, that means a special meaning that is reserved for convolution. So convolution is defined as the integral a lambda d t minus lambda. So this is a dummy wave. So I can call it tau, I can call it mu, I can call it lambda, I can call it x. It doesn't matter what I call it. What's important is the form. It appears here, it appears here, and it appears here. Just a dummy. So today we will go through a crucial theorem. It's called the Fourier transform property of convolution. Extremely important, right? It's one theorem, and we will limit the lecture to that one theorem because it is so important. It is one of the most important things that we will learn in the course. Okay, so it deserves a special day, which is today. We will focus on that only. Very, very important. So what we are going to learn is the Fourier transform property. So what is this magnificent property? Let's say we have two waveforms, x of t as a Fourier transform pair capital X of x. Y of t is a Fourier transform pair capital Y of f, where these are complex functions. So in general case, x of t, y of t, x of f, y of f are set of complex functions. The domain and range are both complex. Sorry, not the domain. Domain is real. So P is real. But the values range is complex value, right? So the property of Fourier transforms is that if you have two individual functions, x of t and y of t defined in time, right? And their corresponding Fourier transforms are x of f and y of f. If we find a new function, let's say u of t with the Fourier transform capital U of f, where u of t is defined as x of t convolution y of t. We can say something about capital U of f. So by definition, small u of t is the convolution of x of t and y of t, right? So you take these two individual things, which has two individual Fourier transforms, and you take the convolution in time domain, and you can find that the Fourier transform of u of t, which we call capital U of f, is equal to x of f times y of f. So what we are saying is the Fourier transform of x of t convolution y of t is equal to x of f. It's a very, very important result because what it basically tells you is that convolution in time domain has a corresponding Fourier property of multiplication, right? Convolution in time domain is given by multiplication in the frequency domain. It transforms convolution to multiplication. So in a different way, stated a different way, for the same operation, right, convolution appears as convolution in time domain and multiplication in the frequency domain. But these are completely the exact same thing in the physical domain, right? So if you have two things in a box, in a circuit that's implementing time domain convolution, it is at the same time described by multiplication in the frequency domain description. Same operation, just the way you look at it. Like when you look at it in time domain, that operation looks like convolution. But when you look at that behavior in the frequency domain, it appears like it's multiplying two things together. Okay. So we'll prove this. So this is again extremely important. It is the basis of filtering in circuits. Right? That's how filters work. So I'll let that sink in for a second, and then we can.
Just
Yeah.
Fourier transfer of u of t gives x of f times y of f.
Yes. Where u of t is the convolution of x and t and y. So I'll leave this part as is and I'll place here. And we'll prove this. It's not difficult to prove. So we know that x of t convolution y of t is equal to integral from the definition of convolution, x of t times convolution y of t is equal to integration from negative infinity time to positive infinity time. Tau is a dummy variable, x tau y t minus tau dt. So we take the Fourier transform of both sides, right? So I'm going to take the Fourier transform of xt convolution by t, which is equal to the Fourier transform of integral right. If I have an equation, I can do whatever I want to the left hand side, as long as I can do the same thing to the right hand side, right? So because it's an integral, I take Fourier transforms on the left hand side and the right hand side. That's a valid operation, right? So let's define what we are trying to do. So we are trying to find the Fourier transform of this. So if I write out the definition of the Fourier transform, negative infinity to infinity, right? Then I have this thing inside, e to the minus j 2 pi f t dt, right? That's the Fourier transform part. Now I stick in the convolution. So the integrals are both going from negative infinity to infinity. So the order doesn't really matter. So I'm going to write it as a double integral. Right. I'm going to write x tau by t minus tau, okay, e to the minus j 2 pi f. Instead of t, I'm going to write t minus tau. I added in an extra tau because I want to have t minus tau here and t minus tau there. Okay, but when I do that, I started out with just a t, but I added an extra tau. So I got to get rid of it. So I get rid of it by putting an extra term like so. So see, it's minus minus, so it's plus j2 pi f tau. So to get rid of the plus j2 pi f tau, I have to put a negative j2 pi f tau to cancel off. Then I have the integration limits. Not the limits, the integrals, the differential part, right? Okay, so now I'm going to call t minus tau t prime. It's a dummy variable, right? It's a dummy variable, but so t minus tau is equal to t prime. I take the differentials. dt minus d tau is equal to d tau prime. Tau is a constant as far as t is concerned. So this is 0. So I can write dt is equal to dt prime. So when I do this change of the independent variable t to t prime, right? I changed this part, that's fine. This becomes t prime. What about the limits? The limits are going from infinity to negative infinity, right? So because the limits are stuck at infinity, it doesn't really matter whether you wiggle the end a little bit by tau. It's still infinity. So your limits are still good. So we can write this whole thing in a slightly different way. Okay, so now I'm going to write everything in terms of, I can write it in one step, but I'm going to do multi-step just to be clear. So infinity, infinity. I have x tau, correct? Then I have y t dash e to the minus j 2 pi f t dash. Then I have e to the minus j 2 pi f tau d tau d t dash. So I have two integrals, double integral, one in terms of the variable tau, the other in terms of the variable t dash, right? And then I have two exponential terms which are in tau and t dash. So there's actually a mix of two functions here, all bunched in together. But if I look at it in a shrewd way, I can actually separate them into two different things. I can write the first integral minus infinity to infinity, everything that has the word has the component tau in it, x tau e to the minus j 2 pi f tau d tau. Then the second integral y t prime e to the minus j 2 pi f d prime I kind of pull them together because they are two independent variables. So even though it looks like one big double integral, it's actually two separatable integrals, right? Because the variables are not mixed. One has a function of t dash only, the other part has a function of tau only. So I can pull them apart, right? So when I pull them apart, I get a product, but the beauty of it is that this is nothing but x of f. Why? This is a Fourier transform where I replace the letter t with tau, dummy variable. Right? This is dummy. Similarly, this is another Fourier transform where t dash is a dummy variable. So you can call it Mickey Mouse as long as Mickey Mouse appears everywhere in the same form. It's a Fourier transform. So we don't have to call it t, we can call it whatever the heck you want. But as long as we get the Fourier transforms definition, that's still a Fourier transform. So this becomes y of f. So my result is x of f, y of f, proved. That's the proof. So the Fourier transform, right? So what we ended up is to show that the Fourier transform of x of t convolution y of t is the Fourier transform of x of t times the Fourier transform of y of t. So once you prove it once, you can keep using the result over and over. You don't have to keep proving it every single time, right? So you prove it today, and then for the rest of the life, you can forget about the proof and just keep using. All right. So let's see how this applies to a linear time invariant system. So if you neglected to write it down, don't worry, we are taking notes. Okay, so you get all the notes. Oh, do you have access to Canvas, by the way? You should see everything now on Canvas. Did you guys check? Nobody checked? Please check. Everything should be on there right now. You should see it. All right. So let's take a linear time invariant system. Right? It's got an input x of t and output I'm going to call y of t. And it's got a unit impulse response. H of t. So h of t is the output when x of t is defined as the delta function. So when you provide a unit impulse into the input, the thing produces some waveform out, right? And that defines the whole behavior of the LTI system. So we call it a unit impulse response, simple h of t, right? This is an LTI system.
What is the delta? Delta is just release.
So remember we talked about the delta function, right? So delta function is defined as the integral of delta t. So it's a spike. It basically means you have 0, and then this function jumps up and goes down, but this area is equal to 1 as tau goes to 0. So this is tau. You basically excite the input with a little spike, which has certain mathematical properties, and when you spike the input, a spike input, it produces something coming up, right? So imagine you put in a little waveform like that jumps up and goes like that. So this is my delta t, and then this produces something up. So this is my h of t. So the output, we can prove this, but for now, just take it the way it is defined as the convolution between the input. So this is my input waveform. And h of t is a property of the system. So we are connecting properties of the input embedded in the waveform x of t with the properties of the system itself, right? So h of t is a description, is a mathematical description of the behavior of the system, right? So you're connecting the behavior of the system with an arbitrary input through this new mathematical operator called convolution, right? So stated in a different way, you have a behavior of the system captured mathematically in the small h of t, right? You have a behavior of an input signal captured mathematically in the function x of t, and you want to marry the behavior of the input with the behavior of the system, and that's done through convolution, right? So the output is the amalgamation of the two things, the system's behavior, the description of the system in a very rigorous way, and the description of the input in a very rigorous way, and mathematically combined using convolution to produce the output y of t.
So can we say y of frequency is x of f times h of f?
Yeah, exactly. That's it. You kind of, you beat me to it. But very good. So from the convolution theorem, right, we can take the Fourier transform. You stole my thunder. Of this side is equal to the Fourier transform of x of t times h of t, right? Right, very good. So we figured out how to describe this. So y of t is simply, in this case, y of f is equal to the Fourier transform of two things convolved is equal to the multiplication of the Fourier transforms of the individual components, which is what we proved. So the Fourier transform of x of t is simply x of f, and the Fourier transform of h of t, simple h of t, is the capital H of f. So this is my input spectrum. This is my frequency domain transfer function. Transfer function. So the concept of transfer function is not unique, right? It depends on which domain. So there is a Laplace domain transfer function h of s. There's a frequency domain transfer function h of f. There is a time domain transfer function h of t, right? So you can define any transfer function. It just depends on what your domain of description is. It can be Laplace, it could be Z transform, which we haven't covered yet. It could be time, it could be frequency, it could be so many other things. But regardless, in whatever domain, the relationship between the input and output can be expressed in a multiplicative form, in this case, h of f. It's not always multiplicative, but it's multiplicative in linear time invariant systems for frequency. Yeah. Sorry, what? Oh, frequency domain. Sorry, it's so unclear. I'm sorry. Let me read it. Frequency domain. So I'll give you a flavor of what this means. So let's say you have a typical application, the vertical, right? And let's say you want to build your own radio, AM radio. Radio, yes. Radio receiver. So you have your antenna, right? So let's say example, simple radio. So we have an antenna to get the signal, get the radio signal. So typically we need to bump up the signal because the signal is extremely weak when we first receive it. So we need an amplifier. So say amplifier of gain, let's say alpha. Right. So what that means is if my input is mu of t, my output is alpha times, let's say x. So t. So when you receive a signal, your radio spectrum, the signal from the air that you capture from the antenna is at a high frequency. So we can visualize it in the frequency domain. Let's say this is f, right? As a symmetrical spectrum, let's say this is at C. This is the Fourier transform, right? So this is my x of f. So this is a continuous function. This whole thing is x of f. Not only this part, this whole function is x of f. Right? So typically we call it a band pass signal because it has some band with B. So this is my band. So let's look at how we can apply some of the theorems that we learned in the last couple of weeks. So the first one is we bumped up the signal to alpha times its input value. So if the spectrum was originally this, right? When I bump it up, the only thing that's going to happen is it's going to grow by a fraction alpha. So my output here is going to be something like this. The same shape. I have to be careful to maintain the shape. So this is my alpha times x of f. So that is the spectrum at this point. Right? We did a linear time invariant operation, the simplest possible thing, scaling. We scale the spectrum by alpha. So its frequency domain location is unchanged, right? The shape of the spectrum is unchanged, but it has more power because we bumped it up by fraction alpha. So in terms of power, it's got a fraction alpha squared more power. Because power is proportional to voltage squared. So when you bump it up the height by a fraction alpha, the actual associated power is going as the square of that, which is alpha squared. Okay. More power. It's not the frequency cutoff, it's the center frequency. Yeah. It's centered at FC. So we call it the carrier frequency. I'm kind of oversimplifying it, but because this is the first thing. All right, first lesson. Next, we are going to do one of our operations. We are going to multiply this whole signal by something else. I'm going to multiply this by a waveform, let's say cos 2 pi f naught. I'm doing a multiplication operation. So let's assume that B is small, so that B is much smaller than FC minus. B is the bandwidth. So we know that cos is described as two complex exponentials, one e to the plus j2 pi f naught t, the other one e to the minus j2 pi f naught t. So two things that are rotating in two different directions, right? So we have an e to the plus j2 pi f0 t component plus e to the minus j2 pi f0 t by 2 is equal to cos. So when I multiply these, right, we know from the theory that when I apply this exponential terms in front of x of e to the t, right, what I get here is alpha cos 2 pi f naught t x of t is equal to alpha by 2 e to the plus j2 pi f naught t plus from this. Okay. Times so I can write this as two separate signals, alpha by 2 e to the plus j2 pi f naught t x of t plus alpha by 2 e to the minus j2 pi f0 t x of t. So recall the Fourier transform of e to the plus j2 pi f naught t x of t is simply x f minus f naught, right? And e to the minus j2 pi f naught t. So t is simply x f plus f naught from the previous lessons. So it basically shift the thing by small value f naught, right? Your center frequency is going to be shifted by f naught. So we have a positive shift from this part and a negative shift from the other part. So you're going to get two copies. The first copy is going to be shifted by f0 towards the positive end, right? It's going to be shifted like this, and another part will be shifted down. It's up converted, right? You have a one copy of the spectrum that's going to be up converted, and another copy of the spectrum that's going to be down converted. And the final result at the end of the mixer is going to be two images of the original spectrum, one at a higher frequency that is more by increased by f0, and another copy that is brought down by f0, right? So let's draw it. Let me see, where should I draw? I'll draw it here. So I'm going to draw the two copies in two different colors. Let's start with, this is my spectrum. So originally it was at f0, sorry, fc. That's the original location. One copy is going to be shifted by f0 and scaled by half. So I'm going to get, so this is half x. And then I'm going to get a second copy that is shifted down. Why? One copy is going to go shifted up because of this component, and then another copy because of that component. So the second copy is going to be like this. Same height, but at a different location. So this is my down converted. Copy of x of f, and this is my up converted. So by multiplying by cos, right, I created two copies of the original spectrum. The first copy is going to a higher frequency, that's called up conversion. The second copy is coming down in frequency, that's called down conversion. And both copies are scaled by half because of the way the cost term is defined in exponentials.
Yeah, that's what it's already set.
Yeah, amplitude is set by alpha and by the fact that there's a half. So the final scaling is alpha by 2.
Okay.
So I'm going to erase this part. And I'm going to continue building my circuit, right? So this first spectrum, I'm going to call, let's say this is V of t. So this is the spectrum. So I'm going to redraw it now that you already know what it looks like. This is the spectrum. So V of t has a spectrum. Fourier transform, right? So we are visualizing what's happening to the spectrum in the frequency domain by applying the theorems. Now what do? We have two copies, one at a higher frequency, one at a lower frequency, and these are the two images in positive and negative frequency components. So this central point here, this is my f equals 0 axis. So what I want to do now is I want to get rid of my high frequency component and keep the low frequency component, right? So my high frequency component is this. Right, so this is my high frequency component. And I can remove that by applying a filter, right? I call it a low pass filter. Why do we call it a low pass filter? It passes the low frequency and cuts off the high frequency. So we are going to put in a low pass filter, which has a transfer function that is 0 in the places where the stuff that we don't want exists, and is 1 in the places where the stuff that we do want exists. So this is my h of f. Let's say this is 1 and this is 0, right? You want to apply in a multiplicative way a function that chops off the stuff that we don't want, which is the high frequency component, while keeping the stuff that we do want, which is the low frequency component. So the function has to have a shape which has low value, maybe 0 ideally, in the places of that we want to chop off, and high value normalized to 1, because when we multiply something by 1, we keep it, right? So we have this square wave-like thing, h of f, that we are multiplying this whole output by. So we want to compute here, let's say, h of f times v of f, where v of f is that whole blue line and h of f is the pink line.
H of f is not in the circuit.
I'm not yet, I'm going to put it there, right? So I'm going to put in this is my low pass filter. So it's got an impulse response h of t, and frequency response transfer function h of f, right? It's computing v of t convolution h of t. Impulse response is simple. So my final output will be only having the stuff at the low frequency component of the spectrum. So this is my f, it's my f, it's my original f0, sorry, fc, right? After multiplying by the function, the high frequency component has disappeared, right? So we don't have that part. So I'm just going to show it non-existent. Just filtered off. But we still have the low frequency component, which I'm going to draw. And the spectrum now. This is my x, f minus. So it might sound a little confusing because today is the first day you are seeing this, but the point here is that you can now, you have the mathematical tools to describe very precisely what happens when you have radio signals propagated. You can turn the frequency, scale it up by multiplying, bring it down. You can filter and get rid of parts of the spectrum, and you can define what shape this filter has by carefully designing a filter which has the right small h of t, right? Because this shape is simply a function of small h of t.
I have a question.
Yes.
For the bottom graph, I know you kept the low frequencies, but
Yeah.
You drew a box h of t. Why don't you draw a box down there?
Because the box is multiplying with this blue function.
Multiply.
Right, remember, we are multiplying, right? So h of f times, so this box is something like this. So when you multiply this blue function with the box, there's 0 here. So it chops off these two ears, but it keeps this central part. So that central part is this. So this is my green.
And then how about like between the groups?
Hmm?
The open space in between.
Well, it's 0.
It's 0.
It's 0 value. So when you multiply 0 with 0, output is 0.
Okay.
So I'm going to end here, and we'll continue next time.